Hello everyone. In this video, we are going to understand the concept of thermal stresses. The concept of thermal stress can be counterintuitive at the beginning because you will be approaching the concept from a mathematical perspective. But of course, at the end of this video, I assure you that the concept of thermal stresses can be very intuitive. It's going to be a very subtle concept. I want to do this video in two parts. So let us delve right into the concept of thermal stress. Now, to begin with, let us take a bar. Let us say that this bar or a rod, it's a horizontal bar that has got a length of magnitude L. It has got a cross-sectional area of magnitude A. So I have clearly defined the geometric properties. Let me define the material property. This bar is made up of material that has got an Young's modulus value of magnitude E. Okay, so I have clearly defined the geometric properties. I have clearly defined the material property. Okay, what is next? Now, let us imagine that this bar is in deep space, far from any gravitating objects. There is no disturbance absolutely. In deep space, what we are actually going to do is we are going to increase the temperature of the bar. So to begin with, let us say that the initial temperature of the bar is T1, and we are going to increase the temperature from T1 to T2. Since we are increasing the temperature, T1 is going to be greater than T2. Now, what happens when you increase the temperature? Well, it's going to expand. Now, I'm going to represent the expansion by this dashed yellow lines. Okay, I'll use yellow here. So the dashed yellow lines represent the expansion of the bar. Now, it is going to expand on either side. Now, there is one assumption that I'm going to make in order to do the calculation in a very conducive manner. I'm going to make one assumption, and that assumption is I'm going to assume that this bar is one-dimensional, which means that I'm going to assume that this bar is going to expand only along the x-axis, which is the horizontal axis, and any changes in dimensions along the y-axis and changes in dimensions along the z-axis, they are ignored without incurring any serious error in mathematics. So that is one assumption that I'm making. Allow me to make that assumption in order to get across the concept. Now, the expansion on the right side of this bar, let us say that it is del L, okay, dl1, okay, suffix 1, and the expansion on the left side of the bar, let us say that it is dl2. Now we can define something called a strain. So what is strain, by the way? Strain is change in length divided by original length. Strain is denoted by the notation small e. So change in length, what is the total change in length? It is dl1 plus dl2 divided by original length, which is L. So dl1 plus dl2, simply I can call that as dl divided by original length. So definitely I can define something called a strain. It is very tangible, it is very palpable. Definitely you can see that the strain is happening. So I can say that the strain is change in length divided by original length. Fine, perfectly fine. Now I can define something called a stress, because stress, what is stress, by the way? Stress is simply Young's modulus into strain. So Young's modulus into strain. So since I have the value of strain, I can define something called a stress, and this is what you will see when you approach this problem mathematically. But let me tell you, if you do this problem in this particular manner, you will definitely get a value for stress. But practically, if you measure the value of stress, if you have an instrument, if you have sensors that you can hook into this particular rod, and if you want to measure the value of stress, the sensor is going to give you the value of stress to be 0. So what is the reason for that? Well, I'm going to tell you the reason, but I have to tell you that this is wrong in spite of the fact that the strain exists. The stress in this case is actually going to be 0. It's actually going to be 0. This is the right answer. I'll be explaining why the stress is going to be 0 in just a moment. But let us say that this is case 1. We are going to do case 2 now. So case 2, we are going to take the same bar. This time what I'm actually going to do, I'm going to take the same bar, but there is one change that I'm going to make. That change is I'm going to fix the bar on the left extreme end. So I'm going to represent that by this blue line. So you are actually fixing the bar. You are actually building the bar is actually built into the wall. It's encasted into the wall on one side, and it is free on the other side. It's like it's a cantilever bar. I should not be calling this as a cantilever beam, guys. Just one bit of information that I want to tell you, because if it is a cantilever beam, then you have to say that the load is acting along the vertical direction. Okay, so it's a cantilever bar. Fine. Now I'm going to increase the temperature in exactly the same fashion. From T1, I'm going to increase the temperature to T2. So T2 is going to be greater than T1. Now what? What is the magnitude of stress? Will there be any stress in this case? Again, this value of stress, let us say, define the value of stress. Now in this case, what is going to happen is I'm going to represent the expansion by the dashed yellow lines. Now what is going to be the expansion in this case? In the previous case, in case 1, the expansion is dl1 plus dl2. What about the expansion in case 2? In case 2, the expansion is still going to be dl1 plus dl2, which means that whatever expansion that you are preventing on the left hand side, because there is a fixture on the left hand side, that expansion is pronounced on the right hand side. That will be produced on the right hand side. So still the expansion is going to be dl1 plus dl2. So now this time, what is strain? I can define something called a strain. Strain is going to be change in length, which is dl1 plus dl2 divide, I'm sorry. So dl1 plus dl2, okay, I can fix that. Okay, dl2 divided by the original length, which is L. So strain still is going to be dl1 plus dl2. Let us say that it is dl divided by original length. Stress in this case should be Young's modulus into strain, but again, this is wrong. Stress even in this case is going to be 0. All right, so that is case 2. Now we are going to do case 3. Now in case 3, I'm going to take the same bar. That's right. I'm going to fix it on the left hand side, and I'm also going to fix it on the right hand side. Now what I'm actually going to do, I'm going to increase the magnitude of temperature from T1 to T2. I'm going to increase the magnitude of temperature. Let me increase the magnitude of temperature from T1 to T2. So this is T1, this is T2. Obviously T2 is going to be greater than T1. Perfectly fine. Now what is going to be the magnitude of stress? What is going to be the strain? The strain in this case is going to be 0. However, the stress actually exists in this case. Stress will manifest in this case. If you have a sensor that you can put here, and if the sensor has to measure the value of stress, definitely it's going to measure the value of stress. So what is happening in case 3? Well, in case 3, what is happening is you are actually preventing the expansion. This much amount of expansion you have prevented on the left hand side. You have prevented an expansion of magnitude dl1 on the left hand side, and you have prevented an expansion of magnitude dl2 on the right hand side. This is the expansion that you have prevented. Now why preventing the expansion can lead to the manifestation of stress? That is the question. Well, I'm going to give you an intuitive explanation. Let us take the same bar. Now instead of instead of fixing it by putting a wall on either side, what you are going to do is you are going to put little green, okay, it's a green men. They will stand here, these little guys, they will exert a force. See, these green men, they are standing and they are putting a force. Now what is that actually they are doing? They are not actually putting the force, but what they are actually doing is they are preventing the bar from expanding, as a result of which they will be putting the force. All right, so the first thing they do is they are trying to prevent the bar from expanding. In order to prevent the bar from expanding, the type of force that they have to apply is compressive force. Inherently it happens that they are applying a compressive force. Now let us say that the magnitude of force they apply is F, and they have to apply a magnitude of force over this particular cross-sectional area. So that leads to the generation of stress, because they are preventing the bar from expanding. If the bar is allowed to expand freely, then these little green men would not be there. If these little green men are not there, then the bar will expand freely and there will not be any stress. So the reason why what is the role of these green men here? The role of these green men, they actually apply a compressive force preventing the bar from expanding. So how much strain that they have prevented? They have prevented a strain of magnitude. The total strain that they have prevented is dl, which is total change in length divided by original length. This is the strain that they have prevented. So I can define something called a stress, which will be Young's modulus into strain. No, not just strain, it is strain prevented. So this is one of the important crucial concepts you have to wrap your mind around when you learn thermal stress. You should not be saying thermal stress. Okay, thermal stress is not just Young's modulus into strain, guys. Thermal stress is Young's modulus into strain prevented. So you should be able to define thermal stress mathematically with its very precise shade of meaning. Don't say it's Young's modulus into strain. Even if you're facing an interview, it is Young's modulus into strain prevented, or Young's modulus into strain arrested, or Young's modulus into strain hindered. Everything, all these are the same. All right. So that leads to the concept of thermal stress. That leads to the manifestation of thermal stress. Okay. So this is the correct mathematical definition of thermal stress. It's Young's modulus into strain prevented or arrested. Now, if the strain is allowed to occur freely, then there will not be any thermal stress. If you look at this particular, in these pictures, I have heard that Eiffel Tower, it grows in its height during the summer season and it contracts during the winter season. Now, is it a good idea allowing Eiffel Tower to grow during the summer season and contract during the winter season? Because they are allowing the engineers, it's one of the towering achievements by human mind, they allow the Eiffel Tower to expand and contract freely. Is that a good idea, or it's not a good idea? I would say that's a wonderful, brilliant idea to allow the Eiffel Tower to expand freely and contract freely, because if they are arresting the expansion, that will lead to the manifestation of thermal stress in the steel structure. Here in the railway tracks, you have to do the analysis of thermal stress, because the railway tracks, they are subjected to extreme climatic conditions, so they can expand and contract, and you have to measure the thermal stress. In part 2 of this video, I'll be explaining how to mathematically compute the magnitude of thermal stress. I will be deriving the formula for thermal stress in the next video. Thank you so much for all your patience. Thank you.